It's now my pleasure to introduce our speaker for today, Dr. Michael Kramer, Director of the Max Planck Institute for Radio Astronomy in Bonn, Germany. Michael has been involved in a number of efforts to use compact objects to test the extremes of physics. Among his many accomplishments, he was involved in the team that discovered the binary pulsar, a system consisting of two neutron stars that orbit each other with a period of only 2.4 hours. In other words, the size of this orbit is about the size of the sun. Subsequent precise timing of the system allowed Michael, Ingrid Stairs, and colleagues to place incredibly tight constraints on any deviations from the theory of general relativity. Michael's also been a foundational member of the European Pulsar Timing Array, one of the international consortia seeking to detect gravitational waves from inspiring supermassive black holes. It's in some sense no exaggeration to state that Michael has written the book on pulsar astronomy, as the Pulsar Handbook by Lorimer and Kramer is one of the staples of the field. Most recently, he's been among the European leaders of the Event Horizon Telescope. Michael today will present a talk entitled Finding the Next Gravity Labs. And without further ado, I will turn it over to Dr. Kramer.
Thank you, Joe. Thanks for the nice introduction, and thanks everyone for the invitation to be able to speak here today. Okay, so I'm a pulsar astronomer. So this talk is going to be about pulsar and binary pulsars as the next gravity labs. So what I'm going to talk to you about today is why do we need to find more of these systems? Where do we expect to find them? How do we find them? And say a little bit about the current state of art and the new surveys that we are conducting in order to find these labs. And then I'll finish with some results and prospects for the upcoming facilities. So let me just put these in context to you. Testing gravity is done by a lot of different experiments. And if you do that, you have to be aware that each of these experiments may test different regimes when it comes to gravitational theories. There is the quasi-stationary weak field regime, where we mostly do tests in a solar system. Pulsars, binary pulsars, but also the S-stars around the galactic center, a supermassive black hole. They test the quasi-stationary strong field regime. That's also true for the EHT image of the black hole in M87. When it comes then to radiative properties, binary pulsars do play a role. The first evidence for gravitational waves came from binary pulsars. But if you really want to study the strong field dynamical regime, you really have to go to gravitational wave experiments like LIGO, but also hopefully soon pulsar timing arrays. And then on a larger scale, on the cosmological scales, you have seen beam measurements. So I'm going to talk about pulsars which test the multi-relativistic strong field regime. And as you can already see from the slides, radio astronomy plays an important role in testing relativistic gravity. It's very useful and complementary to all the other methods. And just to show you this and how useful it is, let me show you that indeed the results of the double pulsar, where we have indeed these two active radio pulsars orbiting each other. And these are the latest results that we just submitted a couple of weeks ago. This is the famous parabola plot that you may know from the Hulse-Taylor pulsar. This is our version for the double pulsar. As the orbit shrinks due to emission gravitational waves, periastron shifts as a function of time. And the red curve is the prediction by general relativity. It's not a fit to the data. And as you can see, it describes the data amazingly well. In fact, it validates GR at the level of about 10 to the minus 4 at the 95% confidence limits. In fact, the precision that we have today is so high that we need to take into account the mass loss of the pulsar due to rotational spin down. As the pulsar loses rotational energy and E is equal mc square, that means that the pulsar loses 8.4 million tons of mass per second. And if you wouldn't take this into account, then our measurements wouldn't be quite fitting. We also do tests that other experiments can hardly do. For instance, LIGO cannot test light propagation effects in strong gravitational fields. We can do this. Here's, for instance, the so-called Shapiro delay curve, which again compares very well to the prediction of GR. And we can do this test now at a so-called 1.5 post-Newtonian level with that system. But how does it compare to other systems? Well, here is a plot that plots the gravitational potential versus the maximum curvature in a binary system. And really the double pulsar is up here with the gravitational wave sources. And many orders of magnitudes stronger curvature can be probed than, for instance, with the images of black holes, at least at the supermassive black holes. So every point in this parameter space basically is able to falsify the theory. And that is why it's important to find more of these systems. And sort of the dream for every pulsar astronomer would be to find actually a pulsar black hole system, which would be really the ultimate laboratory for us to test a GR, but also alternative theories of gravity. And just like in a double pulsar, we can use the pulsar as a clock orbiting in a curved space-time around the black hole, and that will allow us to measure the mass very precisely, the spin, but also the quadrupole moment of the black hole. And if you measure all these quantities, you can test the so-called cosmic censorship conjecture. I'll say a little bit more about that later, the no-hair theorem, and as I said, it's an excellent probe also for alternative gravity. So we have done some calculations, and we have shown that indeed, if you find a stellar mass black hole with a pulsar around it, then you can measure the mass, for instance, to using one of these relativistic effects, which I won't have time to explain, but to a ridiculous low level of 10 to the minus 3 or 10 to the minus 6 precision. You can also measure the spin very precisely. This is done via frame dragging effects, how the orbit changes due to the frame dragging that the black hole that it spins effects on the space-time around it. And again, as you can see in the fractional errors, we would be able to measure this under most circumstances quite precisely. Quadrupole moment measurements are actually very difficult, even for the next generation of radio telescopes like the SKA, like the NGVLA. But things become much easier if you would have a black hole which has a few solar mass, million solar mass as a size. And of course, that's exactly what we have in the center of the galaxy. And that's why we also try to find pulsars around Sagittarius A star. Because if you do that, then you can indeed measure the quadrupole moment and the spin very precisely. And that would lead us, even for slowly spinning black hole, very strong residuals in or changes in the arrival time of the pulses plotted here, so-called residual, as the deviation from an expected arrival time without a binary companion. And you can see the structure is very significant. We would be able to measure the so-called quadrupole moment of the black hole to about 1% precision. And for that, it's even not necessary to have a full complete orbit around Sagittarius A star, but just a single periapsis passage will be sufficient to get that measurement. And here we plot the quadrupole moment, a function of black hole spin. So Kerr black hole would lie on this blue line here. These are simulated data, of course. And again, with the full orbit, you can get a very precise measurement, but even with the periapsis measurement alone, you can constrain the parameter space quite well. And with every other periapsis passage, this arrow ellipse basically shrinks, and you can see if the no-hair theorem, which would be valid if it's on a blue line, is in fact valid or not. And then, of course, you can compare this and combine this with the constraints that you have from other experiments like the S-stars around the galactic center or the upcoming EHT shadow measurement. Then you can actually constrain a parameter space very well, and you can see whether the black hole follows the prediction of GR or not. So that's a very exciting prospect, and that's, of course, one of the motivations why we try to find these systems. So where would you find them? Where would you find pulsar black hole systems in general? Well, if you have two compact stars, a Newton star and a black hole, they can be created in a different way as a binary system, but the most obvious one is that you have two supernovae in a massive binary system that would usually produce a black hole and young pulsar in a wide eccentric orbit, but it's also possible under certain circumstances that you can create a black hole with a millisecond pulsar, recycled pulsar companion that is much faster spinning than a young pulsar. So where would you find them? You would find them because there are two supernova explosions very close to the birthplace if the system hasn't broken up. And that means you will look in the galactic plane where you would also find, for instance, the double Newton star system. So by searching the galactic plane, you will not only have a chance to find pulsar black hole systems, but you'll also find double Newton star systems like the double pulsar or the Hals-Taylor pulsar at the same time. There are other ways of creating pulsar black hole systems, which I won't have time to explain, but you can happily ask me later. But most importantly, we'll find them in areas where you have basically close, very high stellar density, so you get exchange interaction. We can basically produce such systems as apart from the normal evolutionary scenarios. And of course, the galactic center and global clusters are such a place. And of course, we are still looking for the pulsar orbiting Sagittarius A star. And here, even a young pulsar or millisecond pulsar would do the trick to do the experiment that I have just described. So of course, this is a beautiful MeerKAT picture from the Sagittarius A star region. And we do see beautiful supernova remnants, and we see very massive stars like Wolf-Rayet stars. So we know that, of course, massive stars did exist in the galaxies and still exist. And these are, of course, the progenitors of pulsars. So you would actually expect just from those observations to find a large number of Newton stars and hence pulsars in the galactic center. At the same time, if you do some more sophisticated studies like that from Robert Wharton or more recently from Federica Abate, there are very good hints that all these processes lead indeed to a large number of pulsars in the central parsec or so of the galaxy. There's also Fermi measurements which could show which had shown access towards the galactic center region, and some people interpret that as signposts of a large population of unresolved millisecond pulsars, which would also be nice to discover. And of course, as I already said, in large stellar density areas, you can get exchange interaction, so you can all produce all kinds of binary companions, in particular if you want to look for extreme binary systems. This is not an old, I mean, this is not a new idea. We have searched the galactic center for a while. We have not been successful. And I think it was the discovery of the galactic center magnetar that really started all these efforts new again, because the magnetars that are radio loud are very rare, and to find such a rare Newton star emitting radio emission right in the galactic center was actually, I think, a bit of a wake-up call that there should be indeed more Newton stars to be discovered. So the answer to this question, do we expect pulsars in the galactic center? The answer is, I think, clearly a yes. But as I already mentioned, we haven't found them, even though there have been many attempts to do so. And why they're so difficult to find? Well, first of all, the interstellar medium, particularly in the galactic center, is very turbulent. And that turbulent means that we have scattering of the waves coming from the pulsar at this turbulent medium. The waves fronts get distorted, and we get a diffraction pattern, which leads then to multipath propagation. And the scattering tail, which at low frequencies smears out the pulse, and only if you go to high frequencies, you can recover the true pulse shape and have a better chance of detecting a pulsar. If the scattering is too large, the pulse is completely smeared out, and you wouldn't see anything. Then Joe and Jim Cordes in some very similar papers pointed out that the scattering could be hyper strong in the galactic center region, basically washing out any chance to find millisecond pulsars or normal pulsars in the region. But again, the magnetar, I think, opened up some new prospects, because looking at the scattering of the magnetar, which is only a tenth of a parsec away from Sagittarius A star, showed that the scattering can indeed be much smaller than we would have expected from that earlier estimates. Nevertheless, whatever happens, if there is scattering, we cannot remove it, at least not for pulsar searches. The only chance to beat it is to go to high frequencies. And so therefore, this is where most of the galactic center searches have been done lately. But of course, the problem is that pulsars also become much weaker at higher frequencies. Nevertheless, we've done some great efforts. We have now discovered or detected pulsars, not discovered, but detected pulsars at frequencies as high as 138 gigahertz, or even the magnetar even beyond 290 gigahertz. So, and even with ALMA, we have seen, for instance, pulsar like VLA at 90 gigahertz with very high signal-to-noise ratio. We even able to measure the polarization properties of VLA at that frequency. So we know in principle how to observe at very high frequencies in order to find pulsars. There's, however, another effect which also makes things difficult. This is a nice figure by Scott Ransom, where in this plot you can see that the single sort of signal that you have when you Fourier transform your data gets spread out and diminished in amplitude if the binary system is accelerating your pulsar and hence changing the period constantly, and therefore you don't have a single spike, but you get this interesting structure in your Fourier spectrum, which of course has much lower amplitude, and therefore it's much more difficult to detect the pulsar. So what you need to do, you basically search over the relevant orbital parameters, which is computationally very expensive or even impossible. So you do some approximations. And here, of course, it helps that we have GPUs now, or even Einstein at Home, other citizen science project to help with the data analysis. But what is important is that you really have a optimal coverage of the parameter space in your orbit. And one way of doing this, I won't go into detail, that's just sort of a teaser. You can use the so-called template bank approach that was invented by gravitational wave astronomers or colleagues, where you can find an optimal way of covering a parameter space that is interesting for you to find a pulsar black hole system. And this is, for instance, the result of a PhD thesis. A student has studied the galactic plane survey with the Parkes telescope that was done early on some years ago. The galactic plane is better seen in the southern hemisphere. That's why we used the Parkes telescope at the time. But of course, now we have other telescopes like MeerKAT, and we'll come back to that in a second. We also, of course, have gone to high frequencies in order to search for pulsars. This is some paper we have just submitted a couple of weeks ago, where we describe Effelsberg searches at 5, 8, 14, and 19 gigahertz. And we still haven't found any pulsar, but what you can clearly show is that most work in the past, when they basically cited or estimated the surface sensitivity, overestimated the sensitivity, in particular for long period pulsars. Here we can see that there's a clear reduction in signal to noise for long period pulsars depending on frequencies. And what you see here basically is the effect of spillover and weather, which becomes more severe at high frequencies. And that's why the effect becomes so difficult, at least for northern hemisphere telescopes. Is when you look at the galactic center, you basically graze the horizon in most of the time. So if the sensitivity curves in further past publications can be looked at, I think you should should take them with some grain of salt. I think the effect has been greatly underestimated in the past. At the southern hemisphere, of course, with ALMA, looking at the galactic center is great because it's basically overhead. And here we use the phased up ALMA at 86 gigahertz to actually look for pulsars in the galactic center. We can easily detect the magnetar with high polarization. And we injected some signals and found the magnetar itself. This is again a sensitivity curve. Everything above the line should have been detected if there would be pulsars, but this is a population scale to the galactic center using a certain spectral index distribution. And so there is again some uncertainty, but we have not found any new pulsar apart from the galactic center magnetar in this search. We do see a similar effect of the long period degradation and sensitivity that we see at other telescopes as well, but it's not as bad as for this case because we're looking right up into the sky. We also searched with picorelator at 84 and 156 gigahertz. This is also a paper that's been out by now. Again, we can use the magnetar to test our pipeline, and we can easily detect that pulsar. We can also inject fake pulsars. And again, our pipeline works across the whole period range, but again, we have not found a pulsar in our data at these frequencies. Of course, 156 gigahertz is a very high frequency to observe pulsars at, so most of them will be just too weak because the flux density spectrum is rather steep. So in summarizing, basically, the complications that we have in looking at pulsars the galactic center at high frequencies, on one hand, at long periods, we run into the red noise, which degrades our sensitivity for long periods. On the shortest periods, we run into scattering and dispersion matter, depending on how strong the scattering is and how good your frequency resolution is. And then, of course, also for the fastest binaries, we are probably or maybe hampered by the motion of them in the binary orbit, which makes it necessary to do acceleration search, so which we may not have done optimally so far. So this is why it's complicated. One thing is also that another thing, dispersion is actually your friend as a pulsar astronomer. That still allows us to distinguish a pulsar signal from radio interference of terrestrial origin. So at high frequencies, you have hardly any dispersion effect, and that makes it much more difficult to distinguish RFI from real signal. So the question is, where's the sweet spot? Where should we look for, in particular, at which frequency we should actually use for our pulsar searches? Well, the answer is actually, let's try everything. So we will use the MeerKAT telescope which of course is a fantastic new telescope built by the South African Radio Observatory. It's 64 dishes, 13.5 meters across, and it's 4 to 5 times more sensitive than Parkes. Of course, the field of view is much smaller, and just doing this for pulsar searches is difficult. So what we've done from the NPIFI is we built a beamformer and a massive pulsar search hardware to convert this telescope into a pulsar search machine, apart from building also 64 S-band receivers. So what we've done is we basically take the signals from the receivers, use the F engine of the correlator stage, pipe this into a massive multi-beamformer, which is built for GPU cluster. You see one of the part of it here, and then we basically have a huge data stream that goes into a transient detection scheme by Ben Steppers in his MeerKAT project, and we pipe the other parallel stream into our binary pulsar search engine, which is basically a big HPC cluster right at the telescope. We do this in the so-called TRAPRON, transient and pulsar with MeerKAT survey, with a number of colleagues probably here on the call being involved. And I won't go into much of the details, but we basically look at supernova remnants, pulsar wind nebulous TV sources. We look at the Magellan clouds, and we've discovered a number of new pulsars in the Magellan cloud already. We look at globular clusters, and we have found tons of new pulsars in globular clusters. And we also find a number of new pulsars in identified Fermi point sources. We also do a galactic plane survey using the equipment from the Max Planck site. And this is just the L-band part that you see here. But in total, we have already discovered more than 50 sources. Again, I won't go into detail, but please visit the website to get an up-to-date list of all the pulsars that we have discovered. And if you have more questions, let me know. We have also found the first probably double Newton star system in the galactic plane. It's a nicely accelerated system, and the masses look quite peculiar, but we're not safe. Shouldn't say this in public because we don't know the results quite yet. Anyway, so this is just to show you, this is basically the L-band survey. And what's important about it is we actually do a fully conventional pulsar imaging and polarization and spectral line survey at the same time. And this is some nice image that we take during the pulsar observations as well. So we do both all at the same time. It's a fully conventional survey. We also do, once all our S-band receivers are commissioned, they are on all telescopes, they are being tested, and the commissioning is going well. So we hope that by the end of the year or so, we can start also an S-band survey, which probes then deeper into the galactic plane because we have less scattering, and looked also towards the galactic center. And here again, this is a beautiful image. The S-band is really, really clean on the MeerKAT side. It's a beautiful dynamic range, and this is a first slide of pulsar data with the S-band receivers on the MeerKAT telescope. And we will spend a couple of 100 hours staring right into the galactic center at S-band to see what we find. So things are still ongoing, and hopefully I can come back and show you some actual discoveries, more extreme binary systems in the plane, and hopefully some pulsars in the galactic center. Certainly, pulsar black hole system would be a superb probe of gravitational physics and would allow us to do all the things I tried to explain to you. We know, I think, where to look. We look at high stellar densities, we look at the plane, we look at the galactic center, we look at globular clusters. We are using MeerKAT as a workhorse, as a beautiful new machine to do this at L-band, at S-band, but I think there's much more scope to go to even higher frequencies, in particular to look at the galactic center. Since so far, the results that we have achieved in the last couple of years are not really constraining, and we will show this in an upcoming publication where we try to summarize all these surveys. But there's still much parameter space left that we can look at where pulsars could still be hidden. And I think one sweet spot is between 30 and 50 gigahertz, where there's a potential population of millisecond pulsars that may have been even scattered at frequencies like 18 or 20 gigahertz. And with that, I thank, but not without thanking all my collaborators, which are too many, and many on the call, which I won't be all list here. But anyway, so I'll stop here and I'll take questions. Thank you very much.
Thanks for that talk. One of the questions is, are there plausible stellar evolution explanations for a deficit of pulsars in the galactic center region?
There have been some proposals by O'Reilly and Dexter, for instance, to say that most pulsars that could develop in the galactic center because of the high initial mass function, other extreme conditions, that we may end up with only magnetars being in the galactic center. That would definitely maybe explain why one of these rare objects that we found, one of the only Newtons, the closest Newtons to Sagittarius A star, has been a very rare radiomagnetar. So maybe that plays in that hand. But on the other hand, you have seen that the other selection effects actually favor magnetar detection over normal pulsar population, which is flat spectrum. Magnetars have a much flatter spectrum than normal pulsars, and you have seen segregation for long period pulsars. So unless you have a flat spectrum that sort of combats that effect, I think magnetars are the most easiest to survive all the selection effects in that sense. So I think I think that argument has gone away. So yes, unless there is from an evolutionary point of view, any difference in terms of converting maybe massive stars straight into black holes, I wouldn't see why there should be any reasons why we shouldn't expect Newton stars. But it's an interesting question, and I think you should ask evolutionary people to evolutionary population synthesis people maybe to answer that question in a more competent way.
Okay. You focus mostly on the frequency range, or a sweet spot in frequency. Can you expand a bit more on what is the need to cover a field of view? How much region around Sag A star is actually needed to be surveyed to make such a constrain the number of pulsars or constrain gravity around Sag A star?
Sure. So if you want to understand the population and maybe even use it for different purposes, for instance, any pulsar population will be a great clock which tells you the history of star formation in the galactic center, because you can determine the age of pulsars. So any age information from the pulsar population would give you a great insight in what actually the stellar evolution in the galactic center is. So for that, you would try to probe at least a couple of parsecs around the galactic center. But if it comes to actually look for the pulsar around Sagittarius A star, you really, it's just enough to just constantly look at Sagittarius A star itself, because the orbits that you're interested in, they are so compact. We're speaking about orbits of less than a year, that you would have them all in one beam if you just look at Sagittarius A star. But if you indeed then look, be a bit more open and also interested in extreme binary systems, again, the first inner few parsec would be the place I would look at in order to get the highest stellar densities. It doesn't mean that you may not be lucky and cover something around this and have a chance to find an extreme binary. But I think you maximize your chances if you really concentrate in the most inner a few parsecs of the galaxy.
Okay, thank you. We are being reminded that ALMA will soon implement a 35 to 50 gigahertz band or suite, which is also known as band 1.
Yes.
Could you discuss a bit about how that might be applied for galactic center pulsar searching?
Yeah, that would be my preferred choice of receivers. We have started with band 3 because that's the receivers available. But yeah, if I had a choice, I would have used band 1 first. And because it could be a sweet spot. We have observed about 2,000 of pulsars at those frequencies, and even with a 100-meter dish in the northern hemisphere, that's with Effelsberg, we've done it routinely. You can do some nice studies. It's certainly the population that you can see in terms of left flux density compared to the steep spectra is much higher at band 1 than it is at band 3. So, and on top of that, if you look at reasonable scattering scenarios, millisecond pulsars are probably still be scattered. I mean, Joe, you may disagree with me, but I think millisecond pulsars will still be scattered around 20 gigahertz to some extent. And so I think 30 to 50 gigahertz band 1 would be a superb frequency to look for, in particular millisecond pulsars in the galactic center. And yeah, maybe because of the many, come back to the initial question, maybe because of the many exchange interaction, maybe we find more millisecond pulsars than normal pulsars in the galactic center because they had a chance to get companions that recycled them to faster spin periods. So that there is, in fact, maybe also good physical evolutionary reason to look at this population of millisecond pulse. And again, yes, I think 30 to 50 gigahertz is ideal to do that.
And while we're talking about schedules for deployments, can you remind us what is the schedule for the full S-band receiver suite on MeerKAT to be deployed and operational?
So all receivers are on a telescope. So we have about 3/4 or so fully operational. We were a bit slowed down because of COVID. We couldn't actually go down to the site and fix those remaining problems. But all the receivers can be remotely controlled from Bonn, and we can even upload new filters. And it's a plug and play system. It's a very nice design. So they are designed, even if something goes wrong, you just take them off, disconnect 2 cables, and that's it. So so we believe that this will make the commissioning quite fast. And as we got the first images, we got the first pulsar light. So my expectation is the commissioning will be completed by the end of the year at the latest. And then hopefully we can start observing with them. But it's a decision that has to be taken by Cereo, but we'll certainly help them any way we can to get our receivers ready by then.
Okay, thank you. Actually, if we go back to the population question, we had one question already about whether there are stellar evolutionary aspects. I think you touched on it, but there's been a lot of interest from the LIGO Virgo community in terms of whether the number of certainly binary black holes is enhanced in the accretion disk around AGN. And do you want to say anything more about either, does that also apply to neutron stars, or what is the tension between the increased stellar densities and possibly large kicks from the explosions that create neutron stars?
Yeah, again, I'm not the world's expert on this, but the thing is, of course, that if you have exchange interactions, the lightest companion will always be kicked out. So you're left over with the most massive companions. So if you have lots of black holes being created, then of course eventually they will kick out all the Newton stars. So that may, if the density is high, you may end up with a higher fraction of binary black holes than black hole Newton star systems. That is sort of my gut feeling what could happen if you overproduce black holes, and if the stellar density is high enough to really have this large number of exchange interactions. But again, I think that warrants some dedicated population study to see how that goes. I've mentioned in passing the work by Federico Abate, who had looked at this a little bit for globular clusters, and they speculate that the same kind of mechanism could indeed be also occurring in the central parsec of the galaxy. So it's a bit of a likelihood analysis, I think, combined with evolutionary scenarios, which I think probably have enough parameters to tune it any way you like. Many years ago, I asked, I wouldn't say the name of the colleague who is an expert in his calculations, and I asked him, was it him, how many pulsar black hole systems I should expect. And the answer was, you tell me, because then we can calibrate our models. So I think it's, in hindsight, everything can be probably explained, but making a firm prediction, I think the error bars uncertainties are quite large in order to accommodate many scenarios. And I think in the past, when I asked this question, people said there could be between 0 and 100 pulsar black hole systems in a galaxy. I think we are probably now to between 0 and 10. And that's why we have the science case for the SKA and, of course, other new facilities, that if you find all pulsars in a galaxy, you find your pulsar black hole systems. But that doesn't apply necessarily to the galactic center. So the galactic center, of course, is interesting still, because you have a really good chance to measure the quadrupole moment, and that opens up many more tests of black hole nature than with stellar mass black holes. But I mean, I wouldn't mind a binary black hole system with a stellar mass, so whatever.
If we think about the standard scientific method, it's you have a hypothesis and you test against it, or you have a series of different models, one of which might be the theory of general relativity.
Mm-hmm.
As you emphasized, general relativity has been already pretty stress tested.
Mm-hmm.
Can you perhaps expand a bit upon what kind of well-motivated alternative, what are the well-motivated options
Mm-hmm.
beyond GR that will
Mm-hmm.
get tested by finding a pulsar or finding pulsars around the galactic center around Sag star?
Yeah, sure. I mean, I think it's a great question. I think the problem is, of course, that we can never prove a theory. If people say this in passing, I mean, they're wrong. I probably said it myself during this talk, but you can never prove a theory. You can only falsify it. You may always find an experiment which contradicts the theory. I mean, think about Newton's theory, and it now becomes really philosophical. It ruled the world, the universe for several hundred years until Mercury came along and decided not to follow the elliptical orbit, and that was the first test of GR that Einstein was able to explain that deviation of Mercury's orbit by curvature of spacetime. So we can only falsify a theory, and probably GR may not be the correct theory given the inconsistencies with quantum theory and the difficulties of unifying these largest and smallest scales. But it's a pretty good approximation, that's for sure. I mean, otherwise it wouldn't have passed all these tests. And it's a very simple theory. It just comes from geometry. On the other hand, so coming to the alternatives, we know a lot of, more or less in every physical context, for instance, you encounter scalar fields. So, and in GR, there are no scalar fields. But if you look at the physics world, scalar fields are everywhere. So why shouldn't scalar fields play a role, at least at some level, in gravitational physics? And indeed, so tensor scalar theory, the tensor for sort of GR plus the scalar, is a very well developed concept of alternative theory of gravity, developed so well that we can actually test it. And in fact, that's another philosophical problem. People can write down alternative theories of gravity, but they aren't actually developed in theory and calculations well enough that we can actually make predictions for experiments. And unless you have a prediction for a theory, the theory is, in my opinion, worthless, because if the theory can't be tested, then, well, it's maybe metaphysics, but it's certainly nothing that we as observers or experimentalists can confront with data. So anyway, this is very philosophical. But anyway, tensor scalar theories are well developed because in particular, people like Esposito Ferrese and colleagues, Damour, they have calculated in particular what the gravitational wave emission, the dynamical features of the theory are. And that we can test very well with pulsar black hole systems, because in this, in almost every tensor scalar theory, I would probably say every, but say almost every theory, you have a violation of the strong equivalence principle, which means that at some level there's a difference of how compact your object is as it moves, sort of behaves in gravitational fields. So if you have a pulsar and you have a black hole, and the black hole is not supposed to have any scalar fields, you have a very strong mass dipole, and you can really test this tensor scalar theory much better with a pulsar black hole system than you can do with double Newton star systems, or even maybe with gravitational wave observation. So there's a very nice paper, Damour and Esposito Ferrese, I think it's 96, who showed that very clearly, that even gravitational wave detectors will not be as good as testing tensor scalar theories than a pulsar black hole system. So, and again, this is a theory which is well developed. It can make predictions, and some of these predictions have been there's sort of a class of tensor scalar theories, and then you compare with the data. So that's certainly one alternative theory of gravity you can test beautifully with black hole pulsar systems, and there are probably others, but many of them are not as developed to actually allow these tests from an experimental point of view. And again, I come back to my philosophical point. And then you have to ask how useful these theories really are if you can't test them.
You have talked specifically about what I might call a classical periodicity search, looking for multiple pulses with a well-determined period. The question asks about, are there other methods? For instance, looking at polarized sources, steep spectrum sources. What are other avenues for finding potential candidates?
Oh yeah, I mean, we did do some, I mean, people have done that before. We have also done it, for instance, Robert Wharton is using the VLA to find circularly polarized sources because they really stand out in among the crowd. Pulsars are among the few radio sources that have a very high degree of circular polarization, not very high, but tens of % sometimes. And so that's an easy giveaway. Deep spectrum sources are also an indicator of underlying pulsars in a point source. And you and Jim were the first one to sort of go down that avenue. So I think, yes, we try every feature that smells like a pulsar to test it, whether it's in the radio or even in Fermi data. When we look at Fermi photons, we basically look at the spectral properties and so on, turnovers and not, and compare it with AGN behaviors at gamma rays, and that's how we select our sources. And I think we do the same in the radio, but maybe not as much as we should have done in the past, but we're getting there. So I think we learned our lessons, and yeah, looking at deep spectrum polarized sources, particular circular polarized sources, is a very nice way, particularly since you don't bother about Faraday rotation, and you don't really know, of course, the rotation measures. So you would need to change. If you look for linear polarization, you would search in rotation measure space as well, but you don't need to do this in circular polarization. It's more difficult to calibrate, in particular if the beam if you have some instrumental effects that can cause it, but it's a worthwhile challenge that I think we're happy to do.
Yeah, it does raise another possibly interesting philosophical question of what if you find something that looks like a pulsar, looks like a duck, swims like a duck, but doesn't quack. Is it a duck? Yes.
Wouldn't that be a great problem to have?
We actually have another science question, which is whether MeerKAT has strategies to follow up LISA detections now when it flies, specifically of ultra compact binaries. And maybe you could say a little bit about what the relevant gravitational wave frequency ranges are here.
Yeah, I mean, I thought, of course, at that time, the SKA should have been swallowed, MeerKAT, and then it's a question for the SKA to decide. But there is a working group for the SKA science working group to look at exactly that kind of issue. So I think the short answer, not specific to MeerKAT, is yes. Whatever MeerKAT will become at that moment of time when LISA flies, is still a few years, will look definitely at follow-up sources in LISA. Frequency range-wise, it's an interesting. There is a variety of sources. Even the double pulsar, probably, I say probably because there are different opinions about this, but certainly is in the frequency range of LISA as a single gravitational wave source. And if you can identify it amid the white dwarf background, you should be able to see it, and at least you know what to look for. And in fact, you can combine LISA observations and, for instance, binary pulse observations to work out the inclination angle of the orbit in a very nice way, because you're basically sensitive to it in a different complementary way. And by combining information, you can work out inclination angle right away if you see it both on the radio and in the LISA frequencies or gravitational wave frequencies in general. So long answer to the short question, yeah, to a one version of the short question is yes, we will certainly do it, or whatever MeerKAT has become will definitely look at LISA sources. It's just a matter of how much observing time it takes, because LISA will locally find lots and lots of sources. So the director or the program, the TAC will have to decide how many time they will give it to LISA follow-up.
And this is, again, perhaps more of a comment, but feel free to comment on it. It relates to the fact that the first millisecond pulsar stood out. It was a very steep spectrum source in some of the original catalogs. And does the number density of, say, highly polarized or steep spectrum sources toward the galactic center perhaps hint that there is an absence of pulsars? Or, well,
Yeah, I mean, I know that there is work going on to identify deep spectrum sources in the MeerKAT image that I showed briefly. And there is probably a catalog. I mean, you yourself have made a nice catalog of deep spectrum sources. You may be better answering that question. But I think there are many ways of mimicking or obscuring deep spectrum sources. But I think the answer, the thing is, if you see this deep spectrum source in an image, it has to be a rather bright source. I think it's fair to say that most pulsars you don't see in a continuum image because it's simply too weak to, we basically dig them out of the noise because they have a short duty cycle and we're tuning into the duty cycle. And if you don't have that information, it is actually not that trivial to find pulsars as the continuum point sources. It's not impossible, but it is not the preferred way of finding pulsars because I think you're still missing a huge fraction of population. I mean, there are people who have repeatedly suggested that forget all of the difficult pulsar processing associated with telescopes like the SKA, for instance, or NGLA or whatever. But for the SKA, I know this statement has been made. And just look at continuum sources and identify this way and follow them up rather than doing an all sky survey with lots of computing behind it. I think this is an alternative complementary approach. But most pulsars that you're really interested in are not strong enough to actually show up in this particular mode of observation. And so therefore, I don't think the sparseness or richness or whatever we see in the galactic centers, the deep spectrum sources, is an indication how many pulsars are there. But that's my personal opinion. You can disagree, Joe, or you can agree, I don't know.
No, I think finding such sources is very challenging. You'd like to be able to do high dynamic range images, high angular resolution in the galactic center at relatively low frequencies, and that's very challenging.
Yeah.
Okay, with that, I think I will draw this session to a close. Thank you all again. Thanks, Michael, for a very fascinating talk.